Welcome to all of you. Now we discuss about multiple choice question from 2019 paper CC-6 Mathematics Honors Semester 3 Ring Theory and Linear Algebra 1. Question paper 2019 paper CC-6. Question 1A. Which of the following subsets of M2R is not subring of the ring M2R plus dot? Correct option is 3, 1A, 0B, such that A, B belongs to the real number, set of real numbers R. Here, M2R is the set of all 2 by 2 real matrices, and let S be the set of all 2 by 2 matrices such that 1A, 0B, where AB belongs to set of real numbers R. Clearly, S is not empty, and if we put A 0 B 0, then 1 0 0 0 also belongs to S, and S is a subset of M2R. Let A, capital A, equal to 2 by 2 matrices, matrix 1A 0B, and capital B equal to 1C 0D matrix, be two elements or vectors of the set capital S, where A, B, C, D belongs to the set of real numbers R. Then A minus B equal to 0, 1 minus 1, 0, A minus C, 0, B minus D. This does not belongs to S, because if a 2 by 2 matrix belongs to S, then in 1 position is 1, and this 2 1 position is 0. But AB, matrix multiplication AB, is equal to 1 C plus D 0 PD. Obviously, this belongs to S. Hence, S is not a subring of the ring M2R with respect to usual matrix addition and matrix multiplication. We know the theorem. Let S be a non-empty subset of R, ring R, where R plus dot be a ring, then S plus dot be a subring of R plus dot if and only if A, B belongs to S implies A minus B and A dot B belongs to S. Question 1b. In a ring R, if A square equal to A for all A belongs to R, then characteristics of the ring R is 2. Correct option is 4. A ring, this is R, this is R. A ring R plus dot is called a Boolean ring if A square equal to A for all A belongs to R. Example, Z2 is the class 0 and class 1 is a Boolean ring, because class 0 square is the 0 and class 1 square equal to 1. Now, A square equal to A, then characteristics of the ring R. Let A belongs to the ring R, then A plus A equal to belongs to R. Obviously, ring R plus is a group obviously, then a plus a equal to a plus a whole square. And by this property, a square equal to a for all a belongs to R. Then a plus a into a plus a. And by right distributive law, a plus a into a plus a into a. That is a square plus a square plus a square. And obviously, this a plus a plus a plus a. And hence, by cancellation law, this a plus a equal to 0, that is 2a equal to 0. Hence, characteristics of R is 2 for every Boolean ring. And what is the characteristics of ring? The characteristics of ring is the least positive integer n if it exists such that n equal to 0. That is a plus a plus a up to n times. And for all a belongs to R, then characteristics are equal to n of the ring R. And the ring R is said to be of finite characteristic. Otherwise, it is said to be of infinite or zero characteristics. A finite ring should have finite characteristics, but an infinite ring may also have finite characteristics. Question 1c. Let C be a set of real valued continuous function within the interval 0, 1, defined on the closed interval 0, 1, with the addition and multiplication of the functions on C0, 1, defined as f plus gx equal to fx plus gx, f dot gx equal to fx gx. X belongs to the closed interval 0, 1, f and g belongs to C0, 1. Then C0, 1, a real valued continuous function in the closed interval 0, 1, is a commutative ring with unity but not an integral domain. Correct option is 1. And this is C0, 1 is the commutative ring with unity. The function ix, that is equal to 1, ix equal to 1 for all x belongs to the closed interval 0, 1 is the unity, that is multiplicative identity for this commutative ring. The function theta x equal to 0 for all x belongs to 0, 1 closed interval is the zero element in the ring. Zero element is the additive identity in the ring. And the ring contains divisors of 0. For example, fx equal to 0, 0 less than equal to x less than half, and x minus half for half less than equal to x less than equal to 1, and gx equal to x minus half for 0 less than equal to x less than half, and gx equal to 0 when half less than equal to x less than equal to 1. Then obviously f not equal to 0 and g not equal to 0, but f dot g equal to 0. So it is not an integral domain. F and g both not 0, but f dot g equal to 0. So it is not integral domain, because a non-trivial ring with unity is said to be an integral domain if it is a commutative and contains no divisors of 0. But here it contains divisor of 0. Here f and g are divisors of 0, contains divisor of 0. Question D. Number of units in the ring Z6 plus dot is 2. Correct option is 2. In a non-trivial ring R with unity, an element A in R is said to be unit if there exists an element B in R such that A dot B equal to B dot A equal to I. I being the unity multiplicative identity in R, and B is said to be a multiplicity inverse of A, and this multiplicity inverse is unique. Now, Z6 is the set of residue classes modulo 6. This is class 0, class 1 to class 5. There are 6 elements in this Z6 in the ring. The ring with respect to the addition modulo 6 and multiplication modulo 6. Class 1 is the unity, multiple identity, and class 2 is the additive identity, that is 0 element. Now class 1 dot class 1, that is equal to class 1, and class 5 dot class 5 equal to 25 class, that is equal to 6 for 24, so residue is 1, so this equal to class 1. So this a dot b equal to b dot equal to is I. So here class 1 and class 5 are the units. Units means multiple inverse exist, non-zero element. So Z6 are 2 units only, and other elements we know 2, 3. Or you can check this. There are 2 units, class 1 and class 5. Next question. Let S plus dot be an integral domain. Let A is a set order pair 0x such that x belongs to S, where 0 is the 0 element of S. Then A, correct option is 2, a prime ideal of S cross S. Here the plus operation means this and dot operation is this. Now we know that a necessary and sufficient condition for a non-empty set I of R to be an ideal of a ring R is A, B belongs to I, non-empty set I of R, and R belongs to smaller belongs to capital R, implies that A minus B and RA and AR belongs to I. Then this I is called ideal of the ring R. Now here S is the S plus dot be an integral domain. Here S is an integral domain, and that is the non-trivial commutative ring with unity that contains no divisor of 0 from the definition of integral domain. Here A is the set of all order pair 0x such that x belongs to S, and 0 is the 0 element of S. Clearly A is non-empty subset of S cross S because 0, 0 belongs to A. Let A, small a equal to 0, x1 and small b equal to 0, x2 belongs to capital A, and x1 and x2 belongs to S. Then A minus b equal to 0, x1 minus x2, that belongs to A, as x1 minus x2 belongs to S. Let R is the order pair Mn be an arbitrary element of S cross S. Then AR equal to AR, this 0x1, this A into M into N, that is 0 into x1 into N belongs to capital A, as x1 N belongs to S. And RA equal to 0, in x1 belongs to A, as in x1 belongs to capital S. Hence, capital A is an ideal of S cross S. In a ring, an ideal P not equal to R is said to be a prime ideal if for some A, B belongs to R, A, B belongs to P, A into B belongs to P, implies either A belongs to P or B belongs to P. Then this P, ideal P, is called prime ideal. This. Now let P, Q belongs to S cross S be such that P into Q belongs to A. Let P equal to A1 B1 and Q equal to A2 B2. Then P into Q equal to A1 A2, B1 B2. That belongs to A because PQ belongs to A. Then obviously, if PQ these elements belongs to A, then obviously first coordinate A1 A2 must be 0, and this implies either A1 equal to 0 or A2 equal to 0 because S is an integral domain which contains no divisors of 0. So obviously either P equal to 0, B1 belongs to A and Q equal to 0, B2 belongs to A. Hence A is a prime ideal of S cross S. Question A. Let R be a ring. Let A is a set of all those 2 by 2 matrix A0, 0, A. A belongs to R. Then correct answer is there does not exist any ring homomorphism from R to A. Either answer option is 3 or question may be wrong. Alternative example, uh, consider the ring R A0, 0, B, where AB belongs to the set of real numbers R under matrix addition and matrix multiplication. And then the map, if maps from the set of all integers Z to ring R, this R is ring and this bold R is set of real numbers, such that if n equal to n0, 0m, where n belongs to the set of all integers Z, is a homomorphism, ring homomorphism actually. Clearly, F is a well-defined map because n equal to m implies this 2 by 2 matrix n0, 0n equal to m0, 0m. And this implies Fn equal to Fm. So obviously, F is a well-defined map. Now for n, m belongs to Z, Fn plus m equal to n plus m0, 0n plus m. That is n0, 0n plus m0, 0m. So Fn plus Fm. And if n into m, this is equal to Fn into Fm. Thus, F is a ring homomorphism, that is homomorphism here. Now, cardinal of F is the set of all those n belongs to Z such that Fn equal to 0, 0, 0, 0. This is equal to the singleton set 0. Next, let A capital A equal to 1, 0, 0, 2. And this is not in the image F, since 1 positions and the 2 positions element are different. Also, A belongs to ring R. Hence, M is not an epimorphism. Question G. Let V be an n-dimensional vector space over a field depth with m elements. Then the number of elements V is correct option is 3 m to the power m. Since dimension of V equal to m, then any basis of the vector space Vf over the field F is given by the set S is the set of all those vectors V1, V2, Vm, and Vi belongs to Vi equal to 1 to m. Now the field F contains m elements, say F is the set of all those elements C1, C2, Cm. Then for any vector alpha belongs to V can be written as alpha equal to C1 V1 plus C2 V2 plus Cn Vm. Then the order n tuple C1, C2, Cm is the coordinate vector of alpha related to the ordered basis B. If we take this basis as V1, V2 as ordered basis, then since any distinct choice of C1, C2, Cn gives us a different vectors of V. Thus, total number of elements in V is given by this C1 uh, can be chosen from this C1 to C2 Cm from the set F. So for first position can be chosen in MOS, and second position can be chosen in MOS, and nth position can be chosen from these M elements in MOS. So we get the M into M into M dot 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 n factors, that is M to the power n. H T maps R3 to R3, Euclidean space R3 to R3, be a linear mapping defined by Txyz equal to x plus y, y plus z, z plus x. X, y, z belongs to R3. Then the kernel of T is equal to the correct option is 3 null set theta. Now, kernel of T is the set of alpha belongs to V where T alpha equal to theta dash, where capital T is the maps from V to W, be a linear mapping from the vector space Vf to Wf, and theta dash be the null vector in W. Let x, y, z belongs to kernel of T. Then x plus y plus z plus x equal to 0, 0 plus 0, because here V is R3 and W is also R3. So this 0, 0, 0, this is the null vector in R3. So obviously we get x plus y equal to 0, y plus z equal to 0, z plus x equal to 0. Hence x equal to 0, y equal to 0, z equal to 0. Hence kernel of T equal to the singleton set theta, but theta is the given by this. Next question I. Let AS maps R2 to R2, Euclidean space R2, and T maps R2 to R2 be linear mappings defined by Sxy equal to x plus y comma y, this order pair, and this Txy equal to x comma x plus y. Xy belongs to R2. Correct option is 2. Ts minus st square equal to ir square, where ir square is the identity mapping on r square. Here S is this, T is this, then Ts equal to T of Sx is x plus y comma y, so this, and T is this, so first coordinate is unchanged and second coordinate is the sum of the first and second coordinate. So first coordinate is unchanged and second coordinate is the sum of this, and st equal to txy equal to this x comma x plus y, and x comma xy is equal to s is the addition of this x plus y, addition of two coordinates and second coordinate unchanged. So addition of these two coordinates and the second coordinate is unchanged. Then ts minus stxy equal to ts is this and st is this, and this minus this minus this. So this is equal to minus x comma y. And then ts minus st whole square xy equal to ts minus st into ts minus st composition of these mappings minus st xy. Now ts minus st xy is this minus x minus y, this, and ts minus st is the xy, so first coordinate is the negative sign and second coordinate unchanged. So first coordinate is the negative sign and second coordinate is the unchanged, so this is equal to xy. Also, so obviously now I R2 is xy equal to xy, identity mapping on this. So obviously ts minus st square equal to ir square, and you can check alternatively this st minus ts square also ir square. Hence st minus ts square equal to ts minus st square equal to ir square. Question J. Value of k for which s is linearly dependent in R3, where s is this 1 to 1, k3 1, 2 k0. Correct option is 3, 2, minus 1. And for the linear independent set of these vectors, we must have this determinant formed by this 1 to 1, k3 1, 2 k0. This is the row is the first vector, second column, second row is the second vector, third row is the third vector. Also, you can write the first column is the first vector, second column is the second vector, and third column is the third vector. This is equal to 0. So expanding this determinant with respect to the first row, and we get this. So k equal to 2 and k equal to minus 1 is the correct option is 3. And note that the set of vectors from R3 in S is linearly dependent if there exist scalars x, y, z not all 0 in a field of real numbers R, such that x this vector plus y this vector plus z this vector equal to 0, 0, 0. So obviously we get a simultaneous set of system of linear equation, this x plus ky plus 2z equal to 0, 2x plus 3y plus kz equal to 0, x plus y equal to 0. In matrix form we can write this is the coefficient matrix into the column matrix xyz equal to the column matrix 0, 0, 0. Ax equal to null matrix. This is a homogeneous system, and since xyz not all 0, so we are interested to find out a non-zero solution of this system. Then we must have this rank of this coefficient matrix A must be less than or equal to 3. The size of this matrix, size of the matrix is n. So obviously rank is less than 3, so determinant equal to 0. So for this non-zero solution, for this linearly dependent, that is the non-zero solutions of this linear dependent for non-zero solutions, so obviously determinant A must be equal to 0. This completes the MCQ. Thank you for watching this video.